This is AP for September 24th. We're going to try to do 3 quick examples. We'll see how quick they really go. Awesome. I keep forgetting that you're calculus students because then I have to deal all day with my honor students where I'm deliberately not using calculus. And I forget that calculus students can deal with math like in a totally theoretical way. So if we have a block, this is like one of the problems that I just gave out. It's being pulled by a rope with a force of tension. It's got a mass M, and we're going to have some friction. Not equal to 0. You know the friction can only be, let's see, friction can only be a positive number, and it's usually can't be less than 1. It's actually possible, more than 1, excuse me. Yes, sir. No, it's flat. We'll say this should be horizontal. We will quickly examine though we're going to say constant velocity. That looks weird, doesn't it? So the block is being pulled with constant velocity. If we free body diagram the block, which we definitely should, okay, I would really encourage you to make a horizontal vector. Oh no. Oh no. Okay. Perfect. So forever after the free body diagram, we're going to treat this as this is really 2 components, ft cosine theta, because we know how to do trig, and then the vertical one is going to be ft sine theta. I really meant to change colors there. Oh, I shouldn't write that diagonal. Oh, it's going to mess up my diagram. Okay. There we go. We got our sine, and then we have ft, just the tension itself, clumsily, on the hypotenuse. Okay, however, College Board will count you off if you put components. They will say, draw a free body diagram with vectors, not components. So you have no choice but to do that one as it is. You're going to have mg pointed down. You're going to have a force of friction pointed back, and you're going to have a normal force. And on this problem, your normal force, magnitude at least, should be less than the magnitude of mg. Why is that? Mr. Jacob? Okay, part of the normal force, the support force, hopefully this is kicking back from last year, this surface, if it was squishy or soft, or if this was liquid, the mass under influence of gravity would just plunge right through the surface. Okay, so the surface is resisting. We call that the normal force because that was Isaac Newton's word for perpendicular. The surface can exert a perpendicular force, we call the normal force, on anything that tries to smash through it. It only exerts enough force to stop that thing from accelerating through it. Okay, that's how structural integrity, that's how surfaces work. Okay, it never exerts any more force than that because it's a pressure equilibrium. So if some of the weight is being lifted by the tension at the angle there, then then we don't have normal force equal to mg. Okay, if we have constant velocity, then we have acceleration equals 0, and that equals the sum of the forces in each direction over the mass. So we can actually do, let's do x in red. So then we just say ax equals 0 equals, so we'll do plus ft cosine theta. We'll do, the force of friction. It will say on your equation sheet, magnitude of force of friction is, it will say less than or equal to the coefficient times the magnitude of the normal force. You're supposed to know what direction those forces have, and it could be less. If we have, like sometimes we could have static friction where you pull but it doesn't move, it has insufficient force. I'm taking the special case where we're at constant velocity, zero acceleration, and I'll explain why in a little bit. Okay, so we have plus force of tension going to the right, we have minus mu times your normal force is going to be mg minus ft sine theta. It's just the weight of the block minus the component that's supported by the rope. Instead, it's minus out front here because it points to the left, and then we divide by the mass. Those are all the x forces. And then on the y forces, ay of course equals 0. That's why I wanted to do ax. We don't rip the block off of the platform. Okay, they would have to indicate that the block can or does escape. So then we have minus mg, that's the easiest y one, but we have to counteract all of those. So we have plus ft sine theta plus the normal force. Which is, oddly enough, this is the normal force. Obviously, because it adds up to 0. So we could solve it, if we didn't know that, we could actually set up the y equation and solve for that, and then plug it back in. Okay. I want to examine really quick, and then the example's done, and you can ask questions. Under what circumstances would ax be greater than 0 or ax less than 0? Because we did it at exactly 0 on purpose. Can this force of friction get much greater? Especially if my angle can't change, if the force of friction has a maximum value of mu mg, right? And actually exerting more tension or a steeper angle, we won't mess with the angles too much. Exerting more tension would actually decrease the force of friction and make it go faster. Okay, so if we increase the force of tension at all, then we should get some, from this case where it's 0, right? We could actually solve this. Okay, and what would we do? We would say if ft times cosine plus, look at that, mu sine theta is greater than mg. Okay, and really, since this mu is usually a small percentage, a small fraction, that's going to be really small. So if ft cosine theta is much greater than mu mg, excuse me, we need to see more of that. We'll do that. If the horizontal component of your tension is significantly greater than what the friction force would be, than your, let's say, maximum friction force. That's if we're not pulling up and we have maximum force implemented. Okay, then we'll have positive acceleration. Okay, and if we have less, then we'll have deceleration. We have to get it started, and then if the friction force is greater, then we're going to slow down to a stop. Okay, and you're calculus students, and you're writing these formulas in your notes, right? So you could just plug them in on the homework if you needed to, right? Okay, well, we talked about. Okay, if basically ft cosine theta is less than mu mg, then ax will be less than 0. Okay. Any questions? this is really a pretty universal formula, because if they added some more tension back, or if they deleted some of these forces, you just use the same equation and just add a term wherever it's needed, or set a term equal to 0 if it doesn't exist. Okay, like you could do theta equals 0, and then cosine of theta is just 1 and sine of theta is 0, so there you go. Okay, that's actually problem 2 from the homework. Theta is equal to 0. You got two blocks connected to each other, but you can do the same quick setup for each block. Okay, there's example 1.